Thank you for letting me into this room. It's very crowded outside. It's a great honor to be stand inside. I will talk about a consulting job I did. First, about some words about me. I did my PhD in computational physics a long time ago. Was involved in projects like Minix for 68K, the mathematics library for Linux. I did the high precision maths. Perl Python porting to the Psion 5, flight gears, flight simulator, did some contributions, and I'm a maintainer for the MSKT util. It's Active Directory Kerberos integration tool. Right now, for the moment, I am the PMC of the Apache Big Data project. More about that later. In my real life, the other life, I'm a software architect for connected e-bikes. And the thing I'm talking about is how to attack a problem when you have to do some consulting jobs and with a big data label on it. And the problem I had to solve was from chem informatics. You have for the development of medical drugs. So the problem at hand is you have a database, a large database of molecules which can be produced quite cheaply, for instance, and you have this medical database of things is written down, for instance, in the SMILES notation. That's a complicated notation to that's the chemical structure of this thing here. I didn't remember the name of it. I just picked randomly one out of it. And the problem is to look for substructures into these molecules which have some healthy, can make you healthy or something like that. So that's not a new problem. There's a commercial solution for it. You throw an enterprise database in it, and you have something like a cartridge in it, and you can make a SQL query, and you get results. The problem is that the duration is very long. For instance, it needs about a day or something. It's not very reliable, and it's very expensive. So the customer looked out for a big data approach to this problem, and fortunately there's an open source project called RDKit. It's a beautiful library for chem informatics, and you can do something like that. You read in a molecule from SMILES, and you put in the SMILES notification, and you have your molecule object, a Python object, and can simply say has a substructure match from the other SMILES notation. So it gives you true or false. That's fine. And okay, so that's always the same thing. We have the ingredients, a time-consuming job. We have a large data set, and make it fast. So, and we have the environment we wanted to use is a big data cluster or an HPC cluster. We have both. So what can we do? So now about talking how not to scale out. You can simply benchmark it when you see that the reading in of the SMILES notation and constructing the molecule object is the most time-consuming thing in this whole problem. And okay, we can simply read it in one time, and dumping the serializing the molecules is called pickling in C in Python. So you can dump it to a file, and so you do not have to reconstruct all the molecules at any time. So that's a huge gain in runtime, but it does not scale anything. It's we are looking out for scale. So in order to make the program faster, throwing more machines in it. So we simply looking at the problem. It's simply an EP problem. It's embarrassingly parallel. So we can simply divide the database into small chunks and throw each chunks at different machines. Quite easy. And the big data approach is to distribute the algorithm to the machines and not the data coming to one machine. So yes, and the beautiful framework for this is the Spark. It's a Spark core, no special ingredients needed. And we use the RDD paradigm, that's resilient data distribution thing. It's called that the files are hacked into different components, so we can distribute it to all the machines. And Spark is beautiful because it runs each on HPC and big data environments. It does not need, is not tied to the HDFS, for instance. So all I did is read the instructions at Spark. I haven't used Spark before, and it's quite easy. We read in a text file. Okay, in fact I'm reading in the pickled file, but we'll forget about it. Text file, I have the input, and I can distribute the algorithm, that's the algorithm here, the function, to the cluster and do some aggregation in order to get benchmarking results. That's all I have to do. As it's, if I remember about constructing an MPI job and thinking what I have to do with all the initialization and it isn't fail-safe. This is inherently fail-safe because Spark handles if a node is crashing or misbehaving or something like that, and only relies on that every node can read that file. So if I have some kind of shared file system, I can distribute it and run it in the environment. So HPC mode is quite straightforward. Use a cluster file system, dump the Spark jar on it, distribute the data in the same directory, and okay, it does not use the locality of data store, but this is CPU bound, not data bound. And we can use the standalone mode of Spark. And okay, let's compare about with the big data setup. Okay, I have to make some advertisement for the Apache Big Data distribution. And only 1 minute left. Okay. Oh yes. Okay, the Apache BigTop is a Debian of big data distributions. It's used by Google, Cloudera, Canonical, and the UDPI. Please turn around, Roman. And it contains all the usual stuff. And it's important to have a compiler environment. We have repositories, we have provisioning with Docker Compose for testing, of course. The OpenStack is broken now, sorry. Had deployment templates based on Puppet, orchestration, if one needs to, likes to have it with Juju Charms. That's the canonical thing. We have an automatic testing environment, and we have non-Intel architectures. And that's a glimpse for our CI compile system. That's the distributions. The Linux distribution center has 7, 6, Debian, Fedora on PowerPC, and Ubuntu on ARM64, and that's something like Hadoop, Giraffe, Hive, and something like that. That's all these big data ecosystem. And it's simply deploying it with the Puppet scripts, use the HDFS, put the data into it, use the yarn mode with Spark, and unpack the Spark 2, because we do not support it until now, and run. Okay, it works. Preview of BigTop 1.2 is we will have Spark 2, but unfortunately it's not finished until now, and we need more help. Please join us at bigtop.apache.org. So let me conclude. The problem runs much better on the HPC environment because it's compute intensive, not data pipeline. That's simply because the big data environment is optimized for throughput, data throughput, not for HPC runtime. So And the problem, it scales really well. It's over n. But unfortunately, if we have, that's the number of machines we put in, and we have some runtime, the total runtime I'm waiting for the job. That's the commercial solution because it's a fixed environment, and our n is, and that one is too much for the customer to pay. So we will have to investigate. Someone has to investigate where we can speed up it much better. Thanks.
Thanks so much. Again, one question. Any questions? One question.